We're about to begin. Okay, very good. So, my name is Phil James. I work at NAFEMA in Tromsø in the north of Norway. I'm the coordinator of the AquaVitae project. And it's my pleasure to welcome all of you here, both physically and welcome to those who are joining us online in this AquaVitae Scientific Conference. It's a hybrid event, as you know, so we are physically here at ATU in Galway. And I'm very pleased to introduce Dr. Deirdre Brophy, who is the Marine and Freshwater Research Leader here at Atlantic Technological Institute, and she's just going to say a few words to open the meeting this afternoon. Okay, nobody could hear me online, so I'm just about to repeat what I just said. Welcome, everybody. Welcome, everybody, both physically and online. My name is Phil James. I work at NAFEMA in the north of Norway, and I'm the coordinator of the AquaVitae project. It's a real pleasure to welcome you into the AquaVitae Scientific Conference, the hybrid event being held here at the Atlantic Technological University. And it's a pleasure for me to introduce Dr. Deirdre Brophy, who's the Marine and Freshwater Research Leader, and she's just going to say a few words of welcome from ATU.
Thanks, Phil. So on behalf of all of our staff and students in the Marine and Freshwater Research Centre here in ATU, I'd just like to extend a very warm welcome to all of the AquaVitae consortium here in Galway and online. It's great to see such broad representation from all across the Atlantic working on this challenge. I'd especially like to congratulate your coordinator, Dr. Phil James, for his leadership of the project, and to thank Professor Gavin Burnell and Chris Pearce for their input into the Expert Advisory Committee. I know that low trophic aquaculture production has an awful lot of potential and can offer huge benefits to the society and solutions towards addressing food security challenges and climate change impacts. So the work of this team, I think, is really important in realising those benefits and in overcoming some of the technical challenges of making that work and making it a reality. For us here in ATU as a technological university, it's been really great to be part of this network that is sharing knowledge and innovation all across the Atlantic. It's great to see this transatlantic cooperation and to be part of it. And it's wonderful as well for our students and other researchers in the centre to be able to contribute to that and to have impact on policy and governance as well. I know you've recently contributed to the Galway Statement and the Belém Statement as well. So really impactful work, really important work that has really far-reaching benefits for society. So congratulations on a very successful project. I hope you've a very productive and enjoyable meeting here. And I hope to see the collaboration continue as well. We as a centre have benefited from Colin's involvement in this project. So I look forward to seeing it continue. Thanks very much.
Great, thank you very much, Deirdre. So I'm just going to give a brief introduction to AquaVitae. Of course, we have many people physically here who know a lot about AquaVitae, but we have some people online, I'm sure, who are interested in learning more about AquaVitae. So just to give a general introduction to what you're going to see in the meeting both this afternoon and tomorrow. Colin? Okay. Thanks for bearing with us. Part of the challenge of a hybrid meeting. So,
apologies. Sorry to interrupt you, Phil. Colin, can you share, because right now what we can see online is the slides, all the slides, and not the main one that Phil is sharing. If you want me, I can go there. If you click on that one where you were, it's just sharing. Yeah, there. Perfect.
all right.
Thanks.
Thanks again. Can everybody hear me online? Yep. I'll take that as a yes.
All good.
All right. The AquaVitae project. The main aim of the project is to unlock the potential of sustainable low-trophic aquaculture in the Atlantic. So we've worked with a range of different species, not just the ones you see in this picture, a range of different processes to produce new products, and they're the things you're going to hear about in the next 2 days. Why are we doing it? I don't think I need to explain to the people in this room or online for that matter that we face some fairly major and significant societal and planetary challenges. Climate change being the one I think that we're all fully aware of, with ocean warming and acidification, and sea level rise affecting most global citizens. Food security is another huge societal challenge, increasing pollutants, loss of biodiversity. And what you're going to hear about both this afternoon and tomorrow is the contribution that AquaVitae can make, not to solving, of course, because these are massive challenges, but we can make a major contribution towards the sustainable production of food and feed, both in the present and going forward in the future. And this is a major goal of the European Union. They have their strategic guideline from published, setting out their strategic guidelines from 2021 to 2030. They explicitly mention increasing low-trophic aquaculture, particularly macroalgae and mollusks. And in addition to this strategic guideline, you can see the small picture on the right there. There was a special event 2 weeks ago, in fact, where people in this room were involved in creating specific pillars, strategic pillars around climate change and other significant issues. So this is an ongoing area of significant interest for the European Commission. That's why they fund projects like AquaVitae. Again, I'm fairly certain that everybody in this room is familiar with this diagram. It's the energy pyramid where we have primary producers on the bottom, fed by the energy from the sun. And as you go up, you have herbivores, first level carnivores, second level, and apex. The relevance of this is that you lose 10% of the energy each time you go up a trophic level. So the lower in that pyramid we can take our food from, the more sustainable that is. You can further break down those species into extractive species like mollusks and seaweed. Of course, they're still fed, they still need feed, they need nutrients in the case of seaweeds, particulate matter in the case of shellfish. But they're quite distinct from fed species where there's actually input into the environment when you talk about their aquaculture. And that interaction between fed species and extractive species is very complex. It's circularity in aquaculture production, and you will hear about that today in the IMTA research areas. The definition of what sustainable LTA is comes from one of the deliverables in AquaVitae. Sustainable low-trophic aquaculture contributes to fulfilling the needs of the present without compromising the ability of future generations to meet their own needs. And you'll see both today and particularly tomorrow when we look at more cross-cutting areas what the positives influences from low-trophic aquaculture are. And I'll just remind you now that if you want more information or if you find anything that's presented today or tomorrow particularly interesting, look us up on the website. You'll see a range of QR codes throughout the talks to find out more information. So the specific value chains we address in AquaVitae: macroalgae, IMTA, integrated multi-trophic aquaculture, echinoderms, shellfish, and finfish. You can see on the right-hand side the areas where the work was carried out. So it was very transatlantic. Within the value chains, we have specific areas of research, 2 in macroalgae, new species in pond culture, offshore kelp. IMTA, we had sea-based, land-based, and pond culture. Sea urchins and sea cucumbers in the echinoderms. Shellfish was mussels and oysters, and we had 2 species of freshwater fish in Brazil, and marine finfish in the relation with feeds utilising low trophic species. These species, processes and products from these research areas will be presented today, in addition to 2 cross-cutting research areas, which is the use of low trophic species in marine feeds and the use of byproducts from low trophic aquaculture. Again, you'll see those presented today. I'm not going to go in details here. This has been posted online. I know the people in the room have it physically in front of them. We will go through those value chains through the course of this afternoon. And then tomorrow we look at more cross-cutting value chain research areas. So we look at technology, we look at defining product characteristics, consumer attitudes, market potential, sustainability, obviously a key aspect of AquaVitae, environmental monitoring and risk assessment, analysis of value chains, profitability and other socio-economic aspects, as well as policy and governance. And overarching all of those, of course, is communication, dissemination, and education, which will also be presented tomorrow. So I hope you enjoyed today. I hope you enjoyed tomorrow's session. If you want to know more, do not hesitate to come and make contact with us, either through the QR codes or through our website. And with that, I just want to once more say welcome to this scientific conference, and I hope you enjoy what we present in terms of results and outputs from AquaVitae today and tomorrow. Thank you. So I'm now going to hand over to Cliff Jones, who is a professor at Rhodes University in South Africa, and he will be our moderator for this afternoon session.
Thanks very much, Phil, and welcome to the afternoon session. The first session is the macroalgae value chain, but before I start, I'm just going to tell the presenters the rules for the afternoon, because I've been told we have to stick to time. So what I'll do is I'll be sitting over there, and I'll also be checking time, and the schedules are quite clearly presented on the timetable. So when your time is nearly up, when you've got 2 minutes to go, I'll stand up. I'll stand over there. When your time is really up, I'm going to come and I'm going to approach you. And when you're over time, I'm going to push you off the stage and take over the microphone so that we can stick to time this afternoon as best we can. All right. We are going to start, as I said, with the macroalgae value chain. And our first presenter this afternoon is Isabel Pinto. Would you like to come up and... Okay, thanks.
Yes, that's the one. And that's here, right? Okay, good afternoon to everyone. And
sorry to interrupt again. Colin, I think it's still sharing the previous slide deck for the people here. Maybe it's better for just share the contents of what you're having right now. Apologies for this.
Oh, that's good, so we know. Okay, good afternoon again. So I'll start with the macroalgal value chain. That is the best one, as we see for the picture that with our coordinator is holding a macroalga. And why do we have that, and why do we think it's important? We think it's important. In the Atlantic, we are still doing very little seaweed cultivation, and we believe that this is an activity that should really increase significantly. Why? Because it allows the production of biomass for different uses, food and other uses, with lower impact, with lower footprint, as we call it, on different areas where we are having problems in our planet, as CO2, nutrients, fresh water, and land for cultivation. So we have two case studies for this. The first one I'm going to present is new species. So one of the challenges we have in the Atlantic is that we have little experience with cultivation that is going mainly in Asia, and so we need to start looking at our species. We don't want to just import the species that we have that are being cultivated elsewhere, so we need really to work on our species. So the first case study we worked with two species, Alva and Codium. These species, we work with them because they are interesting for the food market, and our industrial partner, this is a very small case study with just 3 active partners, and our industrial partner really were very interested. They already have this in production, but in lower production, and they wanted to improve the cultivation of these 2 species. So we're starting with the Codium. So the existing process that they have is that they just fragment the algae and they grow back. So this is how they do the propagation of these algae. So they grow them in small tanks in a fish farm, and they wanted really to be able to seed ropes, another carrier, so they could really increase the area that they can use for this cultivation. So we work on 2 processes, going through sexual reproduction and also micropropagation, so use adult thallus and crush them, enable to seed ropes. So the first one we did at CIMAR, and we actually experiment a lot in how to do this disaggregation of the thallus of the alga to really seed ropes and from different origins, and then to enable them to grow, and then finally to regain the morphology they have in nature and also in the culture of the tanks. And we were able to, these are the conditions, we tested several conditions, I'm not going here in detail. And what we found is that to really do the seeding, all the conditions that we tested actually worked, and very few had significant differences for better or for worse. And also the growth, we managed to have growth in all the conditions tested. But when we want to induce the morphogenesis, so they will go back to the shape and also to the organization, the thallus organization they have in nature and also in the cultivation, we really had to increase significantly water movements and light intensity. So we went then to our industrial partner, to Alga Plus. We sent them and actually worked with them with the protocol we came up with, and they tested it. They also seed some substrates, and they tested, and we also sent them seeded ropes, and they tested it in their ponds with some good results. They are still not producing this, but actually we have a new project starting now. We're going to use this method for producing seeds to strings to be cultivated at sea in Portugal. So then for the ulva, this is the main production of alga plush, still not in, they don't produce a lot. I mean, a lot may differ in different environments, but then they wanted to start having the possibility of producing through the by sexual reproduction. So what happened is that a team in the University of Santa Catarina in Brazil, they tested a protocol to produce this with their local ulva ornoi. And so they tested many environmental conditions to induce the production of gametes, then the fertilization, then the growth of the small seedlings, and so they come up with the process. So this petri dish is the small seedlings they produce after gamete release and fertilization, and then they were transferred to flasks, and different conditions of nutrients and also density were tested to see what was the best conditions for growth. So they got good growth, especially if they managed to change the growth median very often, like daily. Also, this is important for gamete production. They got much better results like that. So they came, so the next task was to use this in the protocol in alga plush with their species that we think is ulva rigida, but we call it ulva sp still. And so for that there was an industry exchange. So Fernando came from Santa Catarina to Alga Plus to use this protocol that they developed in Brazil for their ulva. And although the ulvas are very similar morphologically, this protocol didn't work. He tried several other protocols that were published, and actually they were not able to produce really gametes and to produce this sexual cycle with the ulva from alga plus. This really shows that even species that are very close, they can have very different behaviors. We also did some analysis from the biomass from the seaweeds that are grown in alga plus, and we found actually quite good protein content, especially in ulva, but also nice fat content for a seaweed that have a very low in fat, especially in polysaturated fatty acids. That's also very interesting. Well, high fiber content and also good mineral content. And we are now doing some other analysis like antioxidant activity that will be finished soon. So other output that I would like to highlight here is really from this project was really the capacity building from our students, our young people. So we have 4 in this small case study. 2 from Brazil that came, one to Alga Plus and the other one to CIMAR, and 2 master students from Portugal that saw in some 3 master theses that were done with this case study. So we also produce some model for the MOOC that is going to be presented tomorrow. And so what we think we have as exploitable results is this new protocol to propagate Codutamentorum, first to get it seeded in substrates, and then really to cultivate it. And we are going to use it soon in another project. So with other company, not only with Alga Plus also, but with another company. And the new protocol to propagate this ulva from Brazil, and so probably to be used in Brazil. We also had synergies not only between the partners and but also with other case studies, especially the case study where they used the algae produced in this case study to produce feeds. So take-home message I think we have to recognize that we still are not in control of the cultivation of seaweeds. I mean, there's a few species in the Atlantic that we kind of know how to work with, but all the others really need effort so we can really completely control life cycle and everything, and can really control their production. And also that we need to adapt this to local conditions. Also that I think it was very important to continue this international cooperation, and also the synergy between research and industrial partners. And also last, that this is an activity that needs training, I mean experience. As we are still starting, there's no experience. I mean, they cannot really, our students just read this on books and know how to do it. They really need to be able to experiment and to spend some time doing this so they get the experience. And then with that, I thank you in the name of the team. So the people that participated, these are the main people that participated in this work. Well, another one is here, that is Stephanie, that we're going to hear about tomorrow. And this is all for me now, today. Thank you.
Okay, thank you very much, Isabel. Our next presenter in the same session. What's wrong? Thank you. Sorry, green. Our next presenter in the same session will be Oliver, and we're busy opening up your presentation now. And Oliver's from Ocean Rainforest. So just so that everyone is aware, we're going to hold questions at the end of the session. So we're not going to have questions after every presentation, which is why I didn't open up the floor a moment ago. Sorry, I should have maybe explained that at the start. But we thought that we'd have a discussion right at the very end. If there's a bit of time between value chains, we might take the odd question to fill that time. Otherwise, we will have a discussion at the end. Okay, thanks, Oliver.
Thank you and good afternoon. It's a great pleasure to be here at the final meeting at AquaVitae. I had also had the pleasure to be at the kickoff meeting. In between, our team at Ocean Rainforest has been more active in AquaVitae than I. So I am the CEO, co-founder at Ocean Rainforest, but unfortunately Urde Bach was not able to be here today. She is the one that has worked a lot with AquaVitae during the last 4 years, and Floor Marshman as well. So I'm presenting something that is very much the work of them, just as much as anybody else. And I would like to have, okay, I'll have an eye on the time taker instead of my phone. I would also like to emphasize the project partners in this case study. This has been a collaborative effort, and without that, we would not have been able to reach the results that we have. Fiscaling has, also based in the Faroe Islands, have worked on modeling in the ocean in order to enable us to better work on site selection. Shokoen has also been active in, especially on the supply chain and value chain analysis. And then we have Marifeed and Rhodes University in terms of application, using the seaweed also for feed in abalone. So to go into what we have done, or present some of the outputs of what we have done. I presume you see it online as well. I would like to highlight how does a supply chain in a kind of classical, or the way we view a seaweed cultivation supply chain. We start with a hatchery and seeding process, then we have cultivation in the ocean, then we harvest, and that's what we do in the ocean. Then we start on the processing. We differentiate between pre-processing, and then we have secondary processing. In the pre-processing, we are typically washing or granulating this biomass into a condition where we then make it either storage stable or do extraction. And the storage stable thing can be drying, or you can ferment it, or you can freeze it, or you can do extraction of various bioactive compounds. And then you have a buyer for the product. If we go a bit deeper in each of these green boxes, which has been the focus of AquaVitae, in hatchery, we have again 4 different activities in the hatchery, a number of more activities in the cultivation, and again, when it comes to harvesting. I will not go into detail of this, but this is to provide you an overview of when we are trying to look at the macroalgae or seaweed cultivation, we kind of have to have all these activities in mind, and how do we want to work with this and optimize this. There have been 2 hotspots in AquaVitae that we have tried to focus on, simply because these are hotspots of inefficiency or cost or bottlenecks in our process. So seeding the substrates that we put in the ocean has been one of those, and harvesting the biomass has been one of those. Both very critical if you want to produce biomass, because without good, efficient seeding, you don't get anything in the ocean to grow. And if you have a lot of biomass in the ocean but don't know how to harvest it, there's kind of no point in the whole thing. So outputs from this case study has been that we have been able to, or we have worked a lot first on the seeding part. We did this manually, first with string, as is still being done in many places in Europe. Seeding a string, then wrap it up around a grow line, deploying that. 4 or 5 years ago, we started to work with direct seeding, and we did that very manually. 2 years ago, we started to experiment with a mechanized way of seeding. You see the machine there, the picture on the left. And the seeding season 22-23, we seeded 100,000 meters with that machine. And it has actually very good results. We have been harvesting up to 4 kilo per meter in September in the Faroe Islands from ropes seeding of that machine. And that is good. This is a per meter in vertical lines that are standing 10 meters down the C column. So if you look at 1 square meter, there's 40 kilos of biomass on that line, of those 10 meters. Or on those, and on that square meter, if you depending on how you want to measure it. So that was one output, and we are continue to expand on that into so we are increasing our current speed 1,000 per meter per hour to 3,000 meters per hour this winter. Then we have worked at species, and as previous speaker said, I mean, the species we are looking at in the Atlantic is primarily Saccharina in the north, in the south, Macrocystis. There's absolutely need to look into, that's what we have worked, and that's when it comes to seeding, we have done it on Saccharina and also Macrocystis. It works on both. On the large scale rig deployment, we have also deployed, increased our capacity. So today, our largest cultivation units contain 80,000 meters and span a ocean expression of around 6 hectares, those 80,000 meters. No, sorry, 12 hectares, those 80,000 meters of seeded lines. And you can see the annual yield up there per meter on vertical grow lines. And there you see our harvesting vessel when we are harvesting it. And that leads us to the next hotspot, that's the harvesting. And what we do, multi-annual partial harvesting, illustrated by that scissor that cuts that saccharina leaf. We cut it there and then it regrows. And in that way, we can see the line, leave it in the ocean for 3 years, and we can harvest every year, either once or twice. This is nice, however, in terms of harvesting, complicated. To replace a hand and a knife or a scissor proves to be very difficult, because this thing is very mobile, very agile. You can do a lot of stuff with it. So in that sense, fantastic. Apart from the fact that it's on a human, and you can't scale a human in the way you would like to scale if you had a mechanical device. We have been working on developing that. I don't have any pictures to show you, even though we have lots of prototypes or mock-ups or close to prototypes. We hope that we have something for next year. And we have started with AquaVitae. We continue that development in a new project called CMARC. This is our biggest challenge still. That is harvesting. Seeding we have sold at the hotspots, but the harvesting is still on the agenda. And otherwise, in terms of scaling or cultivating different seaweed species, in the north it's saccharina and macrocystis we believe we can grow. And there are also attempts now in Namibia, not in this project, but in another company. And then we have other species definitely to look into, but there are not many species we are working with in Europe. Another way, another outcome of AquaVitae that has proven to be very useful for us is to come up with ways of doing site selection. And Fiscaling has been responsible for this work, what we have done in the Faroes, and also we did work in Maine. These maps indicate wave, current, and depth. And on the middle map, you see the Faroe Islands. The dots are potential sites according to the criteria we have applied where we can grow seaweed in the Faroe Islands. What we haven't done in these maps is nutrient supply, which is also important when we are trying to do site selection. Site selection is key here. And I think very often underestimated when they talk about seaweed cultivation. You underestimate, you actually need to have the good site with the right nutrient supply and of course the other environmental conditions depending on what species you want to grow and at what scale. Then we looked at the economics, and these numbers then indicate how we can reduce from the current cost, and we have actually numbers here. This is when we started. A fresh kilo of seaweed had a price of 1.60 euros sorry, this is fresh weight, 1.60 euros, and that is far too high to be commercial. Fortunately, we have come down. This indicates how you can come down to around 60 or 60 euro cent per kilo fresh weight. It's still too high. You have to go further down. And the way to go to reduce the cost is mechanized harvesting, being better at cultivating. Even though you put a fresh line in the water, not everything comes out of it. So being sure that you can harvest or get as close to 100% of your potential is important instead of less than that. So in a kind of summary, this is what we have done in the case study 2. And these are all results that we will utilize in the future, are utilizing on a daily basis today. I would say when we look at the collaborate effort in this project, I am using this a lot when I communicate to customers, to investors and others, the carbon footprint of seaweed compared to other food items, close to zero. And this is really why many industries, big industries, are looking at seaweeds to use that as one way to reduce the carbon footprint in the supply chain in order to meet their sustainability goals for 2030, 2040, and 2050. This is why this has a merit in the future as an industry. Take our home messages. The logistical hotspots, the seaweed cultivation, the mechanized harvesting are still something we really have to sort out one way or the other. Increased yield will reduce price together with the mechanization in general. current speed, wave height, depth, and nutrient supply are key for site selection, which are key for cultivation. We can do third-year harvest if we get more than 60% or 50% of the potential yield. That's one of the economic analysis that one of the results of those. We can reduce the equipment cost if we reuse equipment. That's another one. That how can we reduce or improve the LCA, the life cycle assessment, by reusing equipment? Yes, we can. It doesn't show that much in the economics, but it shows in the LCA. And then it's practical things regarding how we do cultivation in the ocean in terms of utilizing space and their line spacing, and it has an impact. I think I am more or less on time now. Thank you very much.
Okay, that brings us to the end of the first value chain. We're now going to move on to integrated multi-trophic aquaculture. And the first presenter will be Jason from Spain. It will be followed by myself from South Africa, and then Felipe from Brazil. So I think I'll let Jason introduce what IMTA is.
Okay.
And her.
Okay, thank you very much. Good afternoon. So as Cliff indicated, I'll start by defining the integrated multi-trophic aquaculture, the value chain, and this will be useful for the rest of the case study that will be later presented. So here with this illustration, what we want to focus on is on the fact that integrated multi-trophic aquaculture is a circular production process, meaning that, as you can see on the slide, some fed species are releasing into the surrounding environment some water that is enriched with Shall I start again, or I can continue? Okay. So the water is enriched with organic matter and nutrients. This organic matter can then be further used by filter feeder species or detritivorous species, while the water enriched with inorganic nutrients can be further used by photosynthetic organisms. These photosynthetic organisms will be able to produce some biomass by using these nutrients, and they will also release a water that will have further less nutrients, and this water can then be reused to produce other species. The biomass by the photosynthetic organism can then be directly used as a source of feed for some species, or can be integrated into compound feed that can then be used also to feed some other species. So basically, the interest of IMTA is that it's a concept. So this concept can be applied to land-based or sea-based system, open or recirculating system, and systems that are using fresh water, brackish water, or seawater. And then in the continuing case studies, you will have more details about these different systems. So I'll start by presenting the one that was focusing on land-based integrated multi-trophic aquaculture. For the development of the different activities, we counted on the participation from partners located along the Atlantic, partners coming from academic or the industry. And they were mainly located in Europe, Spain, Germany, France, and then South Africa. To develop the activities, we also counted with the participation of associated contributors that were also based in institutions located in the same geographical areas. So for the land-based production, the land-based IMTA production, the focus was on abalone, sea cucumbers, and macroalgae, tackling hatchery, nursery, and grow-out stages, while focusing on the resource utilization, waste management, and nutrient cycling. The results that were obtained contributed to the development of different deliverables. You can have access to the deliverables with the QR code, which is on the left of the screen. And the results also contributed to other associated components of the value chain, such as the regulatory and policy documents, the environmental monitoring indicators, and the education and outreach materials that were produced within the AquaVitae project. So during the hatchery, we focused on the optimization of hatchery protocols for abalone in order to increase the reliability of seed production and also to have some protocols that could comply with organic certification. The results were presented at different scientific symposium, and actually there is a paper that is in review that is synthesizing the different results. At the nursery stage, we looked at the possibility to apply the IMTA concept from the early stages, since the nursery. This allowed to have some new products that could be produced together with the abalone and that could allow a diversification of products from early stages. The experiment also looked at the climate change effect during the nursery stages for abalone production, and this in order to obtain some future adaptation protocols at higher temperature when these are going to happen. This also enabled the production of a scientific article. And during grow-out, so for the grow-out, different experiments were performed at different geographical locations at the same time, and they focused on the integration of multiple low trophic species in the land-based IMTA system. Basically, we focused on abalone and sea cucumber in order to diversify the low trophic species production, to increase the bioremediation and waste utilization, especially by the sea cucumbers. This allowing to have a new product at no additional cost for the producer, and also at the same time to reduce the environmental impact of the production. The results were also presented at different symposium, and an article is in preparation. And then for grow-out, the other experiments that were performed focused on the development of an innovative feed for abalone. The innovation came from the fact that we tested the integration of IMTA-produced macroalgae in the compound feed. This in order to improve the feed sustainability while reducing costs, and at the same time improving the abalone growth. As the results were synthesized and are now in preparation to have a scientific article being produced, and they also allowed to perform a life cycle analysis for land-based IMTA centered on abalone, and the result highlighted the interest of the innovation to contribute to energy saving during the production process. And finally, we've analyzed different products that were produced in these different land-based IMTA system. This in order to find out about the nutritional quality of the new products. We found out that the sea cucumbers that were produced in the systems were not showing any significant difference in terms of approximate biochemical composition and fatty acid composition in comparison to wild specimens. And also, the analysis were also made in order to improve the products that are actually being produced in IMTA systems. So, as indicated at the beginning, these multiple experiments were performed along the Atlantic, and they enabled to have a lot of exchange between the partners, and they also enabled to have a lot of exchange between case studies, and they promoted knowledge transfer between industry partners that were involved in the activities, student transfer, so they were really fruitful in terms of exchange. So as a synthesis, we found out that IMTA is applicable in systems that are integrating exclusively low trophic species, and that these can be applied from the nursery stages. So basically we found out the macroalgae that were produced in the land-based IMTA system were of high nutritional quality. They allowed their integration in compound feed, and this compound feed was able to sustain good abalone growth. And at the same time, they allowed the production of a new product, in that case, the sea cucumber. But IMTA did not only integrate species, it was also a great way to integrate partners, to integrate people from different regions, and to have very fruitful exchanges between the people. And this also contributed to transferring the IMTA processes all along the Atlantic. In the future, not only for land-based IMTA, but for IMTA in general, we think it would be interest to have the environmental contribution of each of the species that are integrated in the system and their compatibilities between each other. Of course, it would be of interest to have large-scale IMTA trials to test the feasibility of the concept and find out the possible difficulties that would be observed when moving on to industrial scales. And of course, it would be absolutely required to have some policies that are enabling the implementation of IMTA in the different regional locations. Thank you very much for your attention, and on behalf of all the team that was behind this case study, all the various teams from all along the Atlantic, thank you very much. It's been very interesting to collaborate.
Okay, the next speaker will be Cliff Jones. It's myself. Can we just check with the with our online guests? Is the slideshow correctly shared?
Yes, everything is fine on this side.
Much.
Thank you.
Okay. I decided I'd say that so that I don't get interrupted. All right. Good afternoon again. I'm not going to introduce IMTA again. It's already been introduced to you. I think, thank you, Jasant. You gave a really nice lesson in introducing the concept. But before I do get going, I want to just mention that I'm up here speaking on on behalf of a really large team. I'm not going to mention anyone by name. I hope to goodness I've got all the contributors up there. If I don't, I apologize in advance. But it was a really large case study with a lot of people contributing from all around the Atlantic. So it's a really nice example of a fantastic collaboration. As I said, I'm going to go straight into sea-based IMTA. Jasant's already introduced IMTA. What we do here is it's exactly the same concept, except it takes place in the ocean, as opposed to in tanks and moving water around. So my talk today, you'll see, it's going to be focused on impact. It's going to be focused on exploitation. There's a large focus on, or there will be a large focus on synergies between this case study and a number of other case studies. But overall, I'm going to be talking about the circular economy and how sea-based IMTA fits into and contributes to that circular economy. I'm going to go straight into one of our first tasks, was where in Saldanha Bay in South Africa, we looked at taking macroalgae, producing it on a fairly large scale on existing mussel rafts. And I'm not going to go into a lot of detail, but the long and the short of it is we produced commercial volumes of Gracilaria. It has not been commercialized. There isn't a need at the moment for it, but the technology was produced in AquaVitae. It's there now to be used when the need arises. In addition to mussels, in one of our other, in another part of the world altogether, in fact, now we move across to France, we looked at oyster, scallop, and abalone culture together with macroalgae. And although the scallops didn't show too much promise, there was a lot of promise with abalone, which is already being done on a commercial scale now, with huge potential for oysters. And one of the main take-home messages that we took out of this piece of work was huge reduction in labor costs. And we're also moving towards organic certification. And producing a product that is more reliably available in quantity and in quality. So yeah, just here a couple of pictures of our colleagues in France. As I said, large volumes of commercial volumes of product being produced already. Another aspect that we looked at was integrating oyster and lobster culture, and this was done by up in the Northern Hemisphere again at IVL. And the outcome of this piece of work was basically showing low-tech and inexpensive production methods of producing lobster by incorporating it with a lower, with low trophic species or integrating it. To the best of my knowledge, not yet commercialized, but more work needs to be done here before we get it ready for commercialization, but another really nice piece of work done by our partners at IVL. So then, still in the ocean, we're going to what most of us normally, it's the more conventional kind of IMTA, where we've now got salmon and mussel and culture in the same system and in a fjord system. So again, this was done by our colleagues up in the Northern Hemisphere. And the real outcome of this, it wasn't just developing best practice to integrate, best practice to mitigate environmental impacts of aquaculture in a fjord system. But it was also done in such a way as, it included modeling. Oh, and by the way, it actually, some of this work was actually done by some of our South African partners as well. There was a nice collaboration here between the guys at Fiscalen and in Stellenbosch University. So yeah, a very different and another aspect of the work. Also done on a large scale with huge potential for application in industry here, making aquaculture more environmentally sustainable at the end of the day. So you'll see I've started to draw a bit of a diagram here. It's circular. All of the bits of work that I've spoken about so far contribute to the circular economy that we were talking about earlier. But what I'm going to do, we didn't quite stop there with the work in our sea-based IMTA. So I'm just going to reduce that slightly, so it's a little bit smaller. I'm sorry, the text is a bit smaller, but we needed to do that because we did so much work in this piece of AquaVitae. For me to fit it all onto one page, small text, so I apologize in advance. So in addition to this, we then took the algae and we want and included it in a feed. So now we're starting to cross-cut into aqua feed development as well. So outside of sea-based IMTA, but as part of our project, it became very apparent that there is risk involved as soon as you start circular or putting feed back into, or putting a product back into a feed. Biosecurity risks, for example. So one aspect of this work looked at developing different technologies or improved technologies to make sure that if you take a product produced in aquaculture and put it back into a feed, you're not going to potentially jeopardize the biosecurity of the stock that you then feed that food, the diet to. This was done, and it was done really successfully in this project. And in fact, this is one of the project outputs that has already been commercialized. It's a process that was commercialized by our industry partner, and right now, they are using it already in industry on a commercial scale. So, so this is the first of actually 3 that come out of this piece of work. We then move on to, who's that guy? Unfortunately, I wanted to. If I had known Phil was going to put an all-black cap on him, I would have put a Springbok cap on him for this picture. But unfortunately, I wasn't given any warning. But we move on to aquafeeds. We move on to aquafeeds. And this is another cross-cutting part of this piece of work where the feed that we took from produced in an IMTA system was then actually put into 2 feed products. Another 2 products that came out of this project that are now currently available on the market, which is, yeah, it's quite impressed with that. So thank you very much to Mary Feed for that. So then I move on to synergies, all right? And I'm now moving away from sea-based IMTA. I'm showing you how sea-based IMTA fits in with a lot of the other work in AquaVitae. So you've already heard what Jasant had to say. This diagram now pretty much circularizes what Jasant presented earlier. I've just put it onto the same diagram because it fits in with ours, because algae that was produced in land-based IMTA also went through the biosecurity process back into abalone feed and back being fed to abalone. But we went a bit further than that as well, and here's that picture's a little bit out of date. This has all been developed since the picture was taken, but I'm afraid it's the only one I had. I need to update it, I'm sorry. That's Wild, another South African industry partner is here today, Wild Coast Abalone. And this is some of the IMTA, the commercial scale land-based IMTA systems that are currently in place, where a lot of this work took place. Jasant spoke about it earlier. But we didn't stop there either. We cross-cut with a number of other projects within the AquaVitae overall project. And the next was taking mussels, byproducts of mussels, broken mussels, mussels that were undersized at harvest, turning them into a mussel meal and into a fish meal. So this is going to be spoken about in a bit more detail later today, but it fits in very nicely and it links with products that were produced in our land-based, our sea-based IMTA systems. And in addition to that, on the same project, also linked with this, not part of our project, but linked with it, one of the nice synergies was the production of paint, where calcium carbonate was included in mussel meal, as a filler in paint. But I'll let them tell you all about that in a little bit more detail. So that's the whole picture. And how the sea-based IMTA fits into a number of other parts of the AquaVitae project. The synergies were absolutely fantastic in this project. Everything, there was knowledge transfer, student transfer, text transfer, all the transfers that were in AquaVitae took place in this case study. It was absolutely awesome. And an incredible opportunity for us in South Africa to work with the large number of people, you guys sitting here really. It's been a wonderful opportunity. So yes, there's been exploitation. there has been impact. So between 79 and 81% of we interviewed 65 people related to our sea-based IMTA. Around 80% of them felt that this work would have economic and environmental impact on economic and environmental sustainability. And 60% thought that this work would be commercialized within the next 5 years. Well, we've already commercialized 3 products from this piece of work, which is not bad going. I've spoken about the synergies. I'm not going to repeat them now. But when you look at everything that I've had to present today, I think we can conclude that there's a big future for developing circular economies further. It's definitely the way to go. Okay, thank you very much. I forgot. I thought I was going to escape the stage, but I'm still chairing the session. So the final speaker in this part of the session will be Felipe, and I'll be moving across from South Africa to Brazil. Yeah, and I'll let you introduce your topic.
Perfect, thank you. Good afternoon, everybody. So my name is Felipe. I came from Brazil. I work at the Federal University of Santa Catarina, that's south of Brazil. And I will present to you guys this multi-trophic system applied to 2 different kinds of systems, the biofloc and organic system. As all the other case studies before me, this is also a group case study. We have many people working in this case study. I would like to name the Primar. That's a farm, that's an organic farm in Brazil that we made many of these studies. Unesp, Embrapa, the Federal University of Santa Catarina, and Federal University of Rio Grande. What I think that's very beautiful about the multi-trophic system is that you can apply it for many different kinds of aquaculture systems. So in this case study, we work in basically 2. One is an organic system at Primar. Primar is a farm in northeast of Brazil. It's the first organic farm producing shrimp in Brazil. They have amazing work there. And here at Primar, the idea was to increase the production by including the seaweed and oyster in the system. For the biofloc, it's a high-intensive production system. And here, we already have the shrimp in the system, that we have low water exchange, but also you want to increase the yield of the system by including seaweeds and mullets in the system. First, I will talk a little bit about the organic system at Primar, that you already know that's an organic farm in Brazil. Here is a picture of the system that we tried with shrimp and oyster. It was very challenging to have the system working at Primar. We don't know exactly why, but maybe for the climate change, the temperature of the water, and specifically the amount of solids in the water have been increased a lot in the past years. So it's kind of difficult at the moment to cultivate the seaweeds on the farm, especially inside the ponds. So during the AquaVitae project, we have to change a little bit the approach of cultivating these seaweeds. So first we are working with seaweeds coming from the sea. So it was very difficult to cultivate them at the Primar, that is a stewarding farm. So they changed for working with seaweeds that were growing at the farm already, so mainly uva species. And also they developed this system that's a laminar cultivating system for the seaweeds. So they're not cultivating the seaweeds inside the tank at the moment. They have it in a system out of the tanks, in a recirculation system, and they are producing pretty well the seaweeds in this new system, this laminar one that was developed during the ecosystem project, the AquaVitae project. And it's very nice also that they're researching and they're continuing the research of what to do with the seaweed that they are producing. And two things that they're doing with a university from Rio Grande do Norte is using the seaweeds for paper and for a plastic from seaweeds. So very interesting research as well. About synergies, At this task, we have a big synergy with the oyster value chain. We will have a presentation about that in a few moments, but they have a lab working at the farm producing the seeds for the oysters. It's a very nice project, and they are working with native oysters from Brazil, so it's a very interesting project as well. And this work for Marcia. Marcia is the owner of the farm. She's an amazing woman. Unfortunately, she's not here with us today. She's in Brazil. And her work has receiving many awards in Brazil at the moment. It's a fantastic work. She was named as Woman in Agribusiness for Exam Journal for Brazil. That's a very important journal for Brazil of the business as a woman in agri-science, in agriculture. Also a destination, green destination of Brazil. It's recognized as an example of farm for the Rio Grande do Norte state. So it's her work is really impressive. Now changing from the bioflocks very different from the organic system. Now we are going to work with a very intensive production system. In the biofloc, we can produce around 5-6 kilos of shrimp per cubic meter, basically with very low water exchange. So it's already a sustainable system by not using a lot of water. But the idea was to include the multi-trophic ideas to the system and to increase the sustainability. So in the biofloc, we have a very rich microbial community that recycles all the nutrients in the system. This becomes this biofloc, and the shrimp can eat this biofloc back. So maintains the water quality and also is a source of feed for the shrimp. During the past year, we have many research about that. We are introducing many species to the system, like tilapia, like mullets, seaweeds, alophyte plants like the salicornia, the sea rosemary, all of them with a very good result when we include it. In all the case, we are able to increase the yield of the system and increase the sustainability by increasing the orientation of nutrients in the system, nitrogen and phosphorus. And right now, we have at the university a pilot system to demonstrate this in a pilot scale production system. So this is a video that was supposed to play. I hope it works. It seems that it's not going to work. Sorry. So in the system, the idea is we have tanks for the mullets, 5,000 liter tanks. We have tanks for the shrimp, 50,000 liter tanks, and we have tanks for the seaweeds. So this keeps going around the 3 species. And when we have a lot of biofloc in the system and we have to take solids out of the system, organic matter, we use this organic matter for the alophyte plants, the salicornia and the sea rosemary. And it's very interesting as well because we are using water from the rain, so we have to replenish the water, that's evaporation from the system, so we are collecting water from the rain. And also we are using solar energy for powering the greenhouse. So it's a very sustainable system. About synergies about this part, we have a big collaboration with the seaweed value chain. So the seaweed that we are using in the system came from the seaweed value chain of the AquaVitae as well. And looking for the circular economy, as Cliff mentioned, we are using this seaweed as feed for the shrimp as well, increasing the immunology of the shrimp. So it's also a circular system. And you are very proud because the restaurants love these products. They call us every week asking for the products, especially the low trophic ones, the plants and the seaweeds. So this is all posts of Instagrams of restaurants and chefs using our products. These 2 here are dishes that are already in the menu of these restaurants, and both of them using products from the university. Especially here, the 2 plants, the alophyte plants, the sea rosemary and the salicornia. And we are very proud when we see this kind of post. This is a post for one of these restaurants. I took the liberty of translating his post. So it says that the new dish of the menu of the Capincho restaurant is a macroalgae tartar with scallop, sea rosemary, and salicornia. The idea is to combine the research advances of the marine shrimp laboratory in one bite. Here we have macroalgae, salicornia, and sea rosemary from the lab of the university. So it's very good for us to have this kind of feedback from the restaurant, from the consumers. And to finish, small joke, I always like to say that it's better than divide and conquer, is to integrate and grow. So I think this is very important to integrate not only the integrated multi-trophic aquaculture, but integrate many actors like we did in the AquaVitae project with industry, the academic world, the consumers, everybody working together to have a better system for producing seafood for everybody. Thank you.
Thank you very much, Felipe. So we are running only about 2 minutes, under. I can't think of the right term to say it. But anyway, we're running early. So we're running ahead of time. And so I don't know if we can take a question or so. It might be a good idea to do that because we are slightly ahead and we're changing topics slightly from all of this algae production. Does anyone have a comment for any of the presenters so far? A question? Nothing at this point. Do you want to do the next?
You can check with the online chat.
Yeah, is there, are there possibly any questions on the chat online?
Not at the moment, but we've informed the participants that there is a Q&A section if they want to ask something.
All right. So yeah, just to repeat again, yes, there will be a question and answer discussion session at the end of this afternoon. So yeah, you can save your questions for there. I think we've used the minute or so that we had. So we are pretty much on time. Hang on, I'm going to need those. So we're now moving from IMTA and algal production to the echinoderm value chain. And we have 2 presenters in this session. The first will be Phil James, followed by Matthew Slater in a few minutes. And I'll let Phil introduce his topic in about a moment, as soon as we've opened it up and shared it.
Great, thank you, Cliff. Good afternoon again. It's a pleasure to give a short presentation on the echinoderm value chain, which involved 2 different types of animal, or 2 different types of echinoderm, sea urchins and sea cucumbers. So I will present the sea urchins, and Matt Slater will present sea cucumbers after that. They're relatively small value chain compared to the other ones. But we have some, I think, very interesting results nonetheless. So sea urchin roe enhancement, myself and Tor Evanson from NAFEMA, who's here, have been working on it from NAFEMA, and Colin Hannon from ATU. And we had a number of project partners. I divide this into 2 different geographic areas. So sea urchin roe enhancement in Norway, our project partners were ourselves, ATU Marifeed from South Africa, and our industry reference group partners were Urchinomics from Norway and Spiny Seafoods, also from Norway. So the general value chain for sea urchin roe enhancement you see here, it involves harvest and transport of the urchins to a normally land-based facility. Then the roe enhancement process itself, utilising specially manufactured feeds, and then transport once more to market and finding a suitable market, let's put it that way, for what is, even though there is a large worldwide market for sea urchins, enhanced sea urchin roe is still a relatively unknown and new product in many of those markets. The other benefit that you get from doing this is, particularly in areas like Norway, we have this enormous biomass of sea urchins. So by extracting these sea urchins, you can do regenerative aquaculture, and you regenerate some of these macroalgae forests that have been decimated by the sea urchin populations, particularly in the north of Norway. And the ecosystem service benefits of that have been very clearly shown over decades now. In Spain, we had a slightly different approach. They harvest and transport quite differently to what we do in Norway. It's a hooker dive setup. They would then transport to land-based holding systems, which was not something that was done before in Spain, through the enhancement process, and then they were aiming to produce out-of-season product in Spain for a different species. This is Paracentrotus lividus. I should have mentioned in Norway we focused on Strongylocentrotus drabacensis. And our project partners, again, were ourselves, ATU and Marifeed in Spain, but we had a very good industrial research partner, AquaVitae in Galicia in Spain. And they weren't doing the regeneration as we were in Norway, but they were very interested in seeding and restocking different areas to encourage the fishery there. So outputs and impact from AquaVitae. Output one were to write and distribute the protocols for the sea urchin harvest itself. And you might think that harvesting sea urchins is relatively simple, but in the far north of Norway, in the Arctic, with permanent dark and some very cold temperatures, it's not as easy as you may think. So we utilised freediving, trapping, and some new technology as well, being designed and developed in Norway. We had protocols distributed, and we were dealing with 13 different stakeholders here for the actual process of the enhancement itself, how we use the feeds, how we test the feeds, and then we did a significant amount of work on the transport, both in air and in water, and we published an article there. We also have a second article looking at the fatty acid and amino acid composition of the enhanced roe, what the health benefits. And we also looked at iodine and heavy metal content in the enhanced roe as well to look at some of the risks of the product as well. Output 2 prototype land-based holding system for sea urchin roe enhancement. We tested 3 alternative systems, geographically diverse. The system on the left is used in Norway, in the middle is used in Spain, and on the right is a system that a novel system that we tested also in Norway. Exploitable results coming from this value chain, production of enhanced Strongylocentrotus. So we had 2 new startup companies begin during the course of the project, expansion of 2 existing companies and diversification of a further 2 existing companies with 1.25 tonnes of enhanced sea urchin that we could put into both Norwegian and European markets. And in terms of Paracentrotus lividus, expansion of the one company that I mentioned there, AquaVitae, to produce both out-of-season product, and also they started to produce seedlings and juveniles to enhance wild areas. And they enhanced 0.75 tonnes of sea urchins, which they then put into local markets in Spain. Some additional activities that we carried out in the sea urchin value chain. We worked very closely with Marifeed, a feed producer, an abalone feed producer in South Africa, and Spiny Seafood, which is one of the startup companies in Tromsø. So we imported a number of diets from Marifeed and tested them in our facility on our species, did some taste testing as well. This was carried out also in Spain. We did it, as I've mentioned, market assessment of enhanced sea urchin roe. There was a very nice taste testing event organised primarily by Avi in Brest, and Avi and France Haliotis was the commercial company that organised that event. It was a really exciting event because we had a lot of chefs come from all around Europe, and they were given these low trophic species to test and play with, and they came up with some pretty amazing products. One of the exchanges, he's not here at the moment, but he'll be joining us tomorrow, is Thomas Juhas. He's a PhD exchange. He came from Cork University to Nofima, and he was looking at fluorescence in a variety of different species, actually, many of them low trophic. So what we were looking at in particular with sea urchins was whether or not you could monitor stress or measure stress in sea urchins by the fluorescence that they exude. Some really interesting work. He's working on writing up that work at the moment. And he tested cucumbers as well, and a range of other species. Some really interesting work on fluorescence there from Thomas. And the sea urchins were included in the business plans, the economic viability analysis, and quantification of ecosystem services that you'll hear a little bit more about tomorrow. And finally, the sea urchin value chain activities in terms of interactions. You can see on the map there that most of the activities took place in Europe, but we had very close connection with Marifeed down in South Africa, and Urchinomics, our commercial partner in Norway, had close contacts with Canada, and we did some tech transfer and testing in Canada as well. So if you want to know more about any of those activities, please don't hesitate to contact me or feel free to go into the AquaVitae project website and look for more information, but I'd be very happy to expand on anything that you've seen here in regard to sea urchins. Thank you.
Thank you very much, Phil. So the next presenter, still on echinoderms, will be Dave. Dave, he says his name is. Matthew Slater.
So much easier with one take. Is that right? Thanks, mate. That's awesome. Hello, everybody here and in the digital world. For those who don't know me, my name is Matt Slater, and I am at the AquaVitae Institute in Northern Germany. And it's a real pleasure for me to be here and to be speaking to you about the sea cucumber aquaculture case study, which is a part of this very important echinoderm value chain. So this is a slightly less prickly topic if we move on to sea cucumbers. And one that I'd like to really note is not so much my work or guidance of my work as somebody relatively old, but more the work of a lot of really fantastic people, Neil Vine and Abigail from Fort Hare University, Colin Hannon at ATU here, and thanks again, Colin, for a wonderful event so far. Luis Sampaio at Furgi, Pete, Cliff, and Helene Senecal, an excellent student from Rhodes University, Dirk at Marifeed for everything, and go the All Blacks, Dirk, that's great, and Daphne Taylor, Richard Clark, and Sanette Petchel from Wild Coast Abalone. And also a big recognition also of the partners in work packages or case studies 3 and 4 who have been involved in this. I think this is unfortunately an older version of my presentation, but I'll do my best going through it. So the tasks that were set out for us within case study 7 for sea cucumbers was initially species selection. That was the first and most important thing we needed to do. So sea cucumber culture and sea cucumber IMTA, both in Brazil and South Africa, are somewhat underdeveloped in comparison to other parts of the world. So we needed to find appropriate candidate species and then undertake a final species selection within the consortium. That began with a literature review, which in the case of South Africa consisted of about 4 total papers available. In Brazil, there was a little bit more. And that pre-required us then to go to expert interviews where we spoke to people that were involved in the industry selling these things or selling similar things in both of the countries, and also aquaculture producers as well as scientists involved in the project. This led to a list of candidate species, and we were able to back up this list of candidate species with some site surveys in South Africa and also visits to suitable sites in Brazil. This led to collections at the sites and also the confirmation then of candidate species based on their morphology and perceived behavioural traits. This was further confirmed by excellent work by both Helene and Abby, looking at the diet or the gut content of the animals, confirming the suitability of the grain size and type of food that they were consuming as sediments, before finally confirming the selection for feeding and breeding of 2 species. Unfortunately, this is not my completed presentation, but the 2 species are Neostichopus grammatis from South Africa and Holothuria grisea from Brazil. Is there any way we can possibly change this presentation, guys? Get the real one? Okay, doesn't matter. The second set of tasks within the case studies was controlled feeding experiments. So that was centered around obtaining the animals, so collection of the animals and then surveying the gut content of the animals. And this was work carried out by Abigail Onormal, and really exceptional work carried out by Abby. And after collecting and surveying the gut content of the animals, Abby actually transferred a large number of the animals to land-based holding facilities, which were made available by Wild Coast Abalone. And so she stored animals in abalone holding tanks without the abalone, but she also was able to construct a very nice experimental controlled feeding facility, or reconstruct it, which allowed her to conduct some controlled feeding experiments. And those controlled feeding experiments were carried out with feeds that were IMTA feeds in the form of abalone feces. They were also IMTA feeds in the form of ulva rigida or ulva SPP, mixed with sand that was being produced in the system at Wild Coast Abalone. Also pellets or waste pellets from the abalone feed. And finally, the sand that was collected where the animals were collected themselves, so ostensibly their natural diet. What we were able to obtain from that work, or was Abby was able to obtain, was a fairly good collection of both growth and survival data, as well as consumption rates, particularly for the abalone waste and abalone waste feed, which is of course important if you're considering cleaning up the waste of a production facility, that you know how many animals you need to actually completely process the waste that's being produced. And the third and final task within this case study was the development of basic hatchery methods. The first half of this task was based in South Africa, and it was based on excellent and very committed work from Helene Senecal from Rhodes. And she was collecting broodstock, and she collected broodstock over a very long period of time, as you can see, more than a year on a monthly basis, and looked at the gonad indices of the animals, and was able to elucidate a very clear gonad index development peaking in September each of the years that she collected, thus indicating probably a spawning period somewhere between August and October. Helene was also able to spawn some of the animals, but was unable to complete any form of larval cycle, which is where fortunately Luis Sampaio from FURG, the Federal University of Rio Grande, came along and in his usual very calm and very capable manner collected some Holothuria grisea north of Rio Grande, quite some distance north of Rio Grande, yes, and he was able to observe a spawning event after collection, and with his very capable team and facilities in Rio Grande was able to feed and follow the full larval cycle of this species in the first go. I think maybe the first researcher that I know that's just picked up a sea cucumber and followed the larval cycle all the way through on the first attempt, and has been able to produce these lovely early juveniles here, which is still present and in small numbers available for IMTA or other further research. So that was the final task within this small little case study. But one of the nice things about sea cucumbers' outputs and impact, this is very old unfortunately, but is we have some good outputs from our sea cucumber activities. Output 1 is holding facilities for sea cucumbers. Very basically, they can be held directly in tanks with abalone, for better or for worse, with very simple cones to protect them. We have diet analyses for Neostichopus grammatis from IMTA, and we have very nice analyses that show that the animals are starkly reducing the total organic matter content of the waste from abalone. So they're removing organic matter from the waste that they feed upon. And that has been published by Abigail and Neil in Aquaculture Environment Interactions, an excellent journal. And very fortunately, the third output, the life cycle closure of Holothuria grisea, which I think will advance its use in culture in Brazil in the future. Additionally, we have some nice exploitable results from the value chain in terms of the testing of bêche de mer from Holothuria forskelii in France, collected kindly by Colin Hannon here, and also taste testing and evaluation of Neostichopus grammatis in Hong Kong, kindly funded by Wild Coast Abalone. Unfortunately, the bêche de mer from Neostichopus grammatis is, I would call it, very low quality, and there's a real challenge there to develop that into a more viable product in the future. The second impact, which may help that, or at least encourage further IMTA of sea cucumbers with abalone, is the very positive impact on farm maintenance costs and abalone growth by the inclusion of sea cucumbers. It's a little small, unfortunately, but this blue line here is abalone growth with the inclusion of sea cucumbers with cleaning of the tanks once a week. So you take the sea cucumber, you take the abalone out of the tank, you clean it once a week. The orange and the yellow are where the sea cucumbers are integrated, but you clean twice a week. There's no sea cucumbers, and you clean twice a week. So basically, if you look at the blue line, you can see that there are two factors that are playing a part here. First of all, the abalone are only disturbed once a week to clean the tank. The second factor is that the sea cucumbers are present and they are removing nitrogen, carbon, a few other things from the system and making sure that the abalone are not disturbed by any negative impact of nitrogenous compounds in the water which they are held in. And what you see is, irrespective of the value of the sea cucumber, a halving of the cost of labour to clean the tanks and an improvement in the growth of the abalone, which I think is very nice because it actually valorises the ecosystem services of IMTA directly to the producer. Additional results, and that's the final result that I'll show, is not the lovely synergy map, but a fantastic network of really, really fun people. Some of whom aren't here because I put their photos in later. I found a really good picture of Pete Britz as well. So, and finally, the graduation of two exceptional students. So I want to put out a special thanks to Abby and Hillian for all their work as well. If you want to know more, contact me or any of our great CS7 partners.
All right, thank you very much. That wraps up the first half of this afternoon's session on the echinoderms. I'd like to take this opportunity to thank the talk speakers from this afternoon. Everybody stuck exactly to time. So thank you very much. I didn't have to come and tackle anyone on the stage. The closest I got was Matt, but ended up it wasn't necessary. So we got a coffee break now. Can I just ask everybody, we're a minute or two ahead, so you've got a slightly longer coffee break. Can you just try and be back a few minutes before 3:20 so that we can start on time and then hopefully stick to time for the rest of the afternoon as well? All right. Anything else, Phil? Sorry? Are there, sorry, before we break up, because we are a minute or so ahead, are there any questions for the presenters from this afternoon? Actually, what I'm doing is delaying you because the coffee is not quite ready. So if there are any other questions, I'll be very happy to take them